Hello everyone. This video we are talking about partial fraction decomposition, section 10.6. This section we deal with rational function. Let's recall what is a rational function. I think we learned this in chapter 2. Rational function is a function which can be written in the form of a quotient of two polynomial functions. So what is a rational function? You see a polynomial in the numerator. You see a polynomial in the denominator. You see a quotient of two polynomials. Then that function is a rational function. Then what is proper rational function? So let's recall what is a proper fraction. So for example, 3 over 4 and 4 over 3. 4 over 3 is improper because the numerator is bigger than the denominator. 3 over 4 is proper because the numerator is smaller than the denominator. Same idea, very similar. Proper rational function is a rational function in which the degree of the numerator, it is a polynomial, remember, is strictly less than the degree of the denominator. One more time. If we have a rational function, the degree of the numerator is less than the degree of the denominator, then the rational function is a proper rational function. In this section, we deal with proper rational functions. We're going to learn how do we decompose a proper rational function. We have two formulas. Depends on the denominator of the rational function. If the denominator of the rational function is a power of a prime binomial, ax plus b is a binomial. It has two terms, right? It is a prime in real number set, means we are not able to factor ax plus b even further. If the denominator of the rational function is a power, the power is mth power of a prime binomial, then we are able to decompose the rational function as a sum of those rational functions, and each single of them has a numerator constant. So the first one is a constant over ax plus b. Second one is another number over square of ax plus b plus a number over cube of ax plus b, all the way plus until a number over the mth power of ax plus b. So that's the first formula. If the denominator of the rational function is a mth power of a binomial, prime binomial, we use this formula to decompose the rational function. Knowing that a1, a2, am, a sub 1, a sub 2, a sub m, those are unknown constants that we need to solve for. Sometimes the denominator of the rational functions is a power of a prime trinomial. So look at the denominator here. Is ax squared plus bx plus c to the power of n. Ax squared plus bx plus c is a prime in a real number set. We are not talking about in complex number set. We have learned in chapter 4, if we consider the solutions in complex number set, then any quadratic equation would have two solutions, right? But we are talking about in real number set. If the trinomial, quadratic trinomial is a prime in a real number set, then we are able to decompose this rational function as the sum of those n terms. The first term, we have a linear polynomial on the top over the prime quadratic trinomial ax squared plus bx plus c. Second term, numerator is also a linear polynomial. Denominator is the square of the quadratic trinomial, and so on and so on. The last term is the last term has a numerator as a linear polynomial, denominator the nth power of the quadratic trinomial. Also know a sub 1, b sub 1, a sub 2, b sub 2, a sub n, b sub n. Those are the unknown constants that we need to solve for. If we know the values for those unknown constants, then the decomposition is certain. So this section, nothing fancy. You just need so good news is everything is open book, right? So you don't have to make effort to remember those formulas. You can just apply it, knowing where do you find those formulas and how do you apply it. Here, there's a question. We are going to learn how do we decompose a proper rational function. For what reason? Why would we learn that? This is very important for calculus. This course, MAT152, is advanced algebra. It's also called pre-calculus. So this technique is very important for you to grasp if you need to take a calculus in the future. When we need to take the derivative or integration, then the decomposition technique it will be needed. Another thing, what about the improper rational function? For example, I have x cubed plus 3x squared minus 2x plus 1 over x squared plus 2x plus 1. This rational function is improper because the numerator has degree 3, denominator has degree 2. The numerator has degree bigger than the degree on the bottom. Then how do I decompose? Do you guys remember in chapter 4, we have learned many theorems to deal with a rational function with a numerator degree bigger than the degree of the denominator. Remember long division. Remember synthetic method. Of course, this one synthetic method doesn't apply. So you can apply the long division to write this rational function as a quotient plus remainder over divisor. So this is a polynomial. And this part is a proper rational function because the remainder always has the degree less than the divisor. Remainder always has degree less than the divisor. So by long division, you could rewrite a improper rational function as a polynomial plus a proper rational function, and then you decompose this proper rational function. It's just like a 4 over 3 can be written as 1 plus 1 over 3. Same idea. All right, so let's look at 3 examples. I hope I could finish the 3 examples in one video. Might not, but we'll try. Maybe I need 2 videos. Let's look at example 1. Decompose this rational function. Numerator x minus 4, denominator square of 2x minus 5. Anybody could tell me the degree of the numerator? Is linear, so it's 1. What's the degree of the denominator? If you multiply out, you would see the denominator is a quadratic, degree 2. So this function, rational function, is proper. Then we are able to apply the formulas to decompose it. Which formula? We look at the denominator. Denominator is the power of a binomial. The binomial is 2x minus 5, which is a prime. So we know we're going to use this formula, the first one, okay? And let's see. F of x equals x minus 4 over 2x minus 5 to the power of 2. By the formula, we are able to decompose it as the sum of 2 rational functions. The first one has a denominator 2x plus 5, minus 5. Minus 5. The second rational function has a denominator 2x minus 5 to the power of 2. right? Because m is 2 here. M is 2 in our case, example 1. So the expansion or the decomposition gonna have 2 terms. And the numerator, a sub 1, a sub 2, unknown constants. So that's how do we apply the formula. Do you think you can do that? Nothing fancy, just follow the pattern. Let me double check. Okay, so unless we know the values for a sub 1 and a sub 2, the expansion or the decomposition is not certain. Then how do we find the value for a1 and a2? This is how do we do that. We copy the left-hand side. We are going to add up the 2 terms on the right. Yes, we are going to add up the 2 rational functions together on the right-hand side. This is a rational expression. This is another rational expression. Knowing a sub 1, a sub 2 are 2 constants. They do not have the same denominator. Then we need to find the least common denominator, right? The least common denominator is going to be the square of 2x minus 5. So in order for the first rational function has the denominator 2x minus 5 square, we need to multiply both top and the bottom by